Yeah, so thanks Michael, thanks Eric for having me today. I started looking at crypto economics about a year ago, and it was like one of the first writings that described Bitcoin in a way that really clearly expressed what it's designed for and what's designed against. And that was during the time where I was trying to gain a more deeper understanding of how Bitcoin works. And it turns out that, so I wanted to read some source code, and it turns out Libbitcoin and crypto economics are both in the same GitHub repository, so it wasn't a far step for me to go. So what I ended up doing was reading up a lot of the source code of Libbitcoin, and in the process, I learned a lot about the difference between protocol implementation, and also about like how you can design software specifically for Bitcoin. So there's some pretty cool trade-offs or optimizations that were made in this project, and I think the goal of today hopefully is to provide you an overview of the tool set, the library. There's a whole server in there, and to express some of that stuff to you today. Okay, cool. So I'll start off with giving you just a quick overview. So a bit of history. The project was originally founded by Amir Taki. You could probably know the history a little bit. But if you look at the source code today, really most of it is written by Eric. A lot of it is really contributed by Eric. It was the first alternative implementation to Bitcoin Core. By being an alternative implementation, there are different design choices made. Some of that we'll cover today. And I think one of the nice things about the project is it's got some really cool design principles which are consistently adhered to. For example, readability, right? Not just the code itself, it's self-documenting code. I think that's something that Eric has put a lot of emphasis on. But the fact that you have a lot of cleanly documented or defined interfaces, you look at the repository or the dependency graph, all these little different modules have their own builds and therefore their own APIs. And so when you get in the project, it's very nice. I can go into, let's say, the Bitcoin system repository, and I can clearly understand, okay, these are all the Bitcoin primitives that are in here. These are the methods and utilities that I can find. So the other thing is, it's really designed to be a performant implementation. You look at the way it tries to parallelize a lot of these tasks, which are potentially inherently serial tasks, and it's also designed to be a performant public server. We'll get into that in a second, and how that differentiates perhaps against other implementations. And obviously scalability is also something that's been ground architected up to be able to deliver. So in terms of the different repositories, we've got the server stack on the right side. You have the node, there's an arrow missing, but the node, which is doing the validation. The server is really just the interface to the clients, the Libbitcoin blockchain, Libbitcoin database, which is a database that's specifically designed for Bitcoin data structures. And yeah, the Libbitcoin system bomb. Very few external dependencies, 0MQ for the server interface, Boost, and libsec P256K1, just like Bitcoin Core. So on the client side, at the very top, we have a tool called Libbitcoin Explorer. Libbitcoin Explorer is pretty neat. It's a command line tool that exposes two things. It exposes a lot of the base library utilities, but it also queries the server. It exposes the server interface. And so what I've done is I have a couple examples in Jupyter Notebook, which kind of demo Libbitcoin, but in doing so we can expose functions in the library as well as in the server API. So I need to walk over to the computer real quick to show this to you. So give me a second while I set it up. Okay, so the first thing I'd like to show is a basic primitive that you see in all wallets, BIP32, HT wallets. And the nice thing about Explorer, what I'm trying to show you here is the Explorer as a command line tool allows me to look at the utilities that are in the library. So for example, HT wallets, XPub keys, HT derivation, these are functions that you see in wallets, but you don't actually get to tinker around with them unless you're writing code. So here's an example where we can do that with a basic bash script. So this is just a Jupyter Notebook set up with a bash kernel, and I'm running bx commands in there. Let me see if I can zoom in to give you a better view. So we've got these very, very fundamental methods. Like we can generate seeds, we can generate a mnemonic phrase, and we can do that on the command line. The nice thing about having in Jupyter cells is obviously we can follow, it's easier to present. But I'm basically creating a mnemonic password phrase here in Japanese. I can create my HD seed 512 bits, and I can do all the HD key derivation that you'd usually have in your wallet, but I'm doing it at the command line, which is pretty nice. So that's what I mean when I say the Explorer tool exposes these internal library utilities very, very nicely, which you perhaps don't often see. Okay, so let me skip to another example. And then, for example, if I'm doing transactions, if I have a wallet that's signing transactions, the wallet needs to query the server, it needs to fetch the previous output, and often that necessitates you having to run a local node. So if I use BX Explorer, it's going to query a server, but because the Libbitcoin server is really designed as a public server interface, there are about, I'm not quite sure, 8 servers that you guys offer publicly, right?
There are
4 testnet.
4 mainnet, 4 testnet servers that are maintained by Libbitcoin.
Right. So if you start tinkering around with Libbitcoin, you build Explorer and you can immediately start querying the blockchain. Use the Libbitcoin Explorer as a blockchain explorer without actually having to run your own node, which is pretty nice. Contrast to that to perhaps the Bitcoin Core server that's really designed as a local node. So that's pretty nice. So here's another example where we're building a transaction. This is an exercise that I use to teach Bitcoin. It's all built around the Bitcoin Explorer. I'm teaching the learners how to sign different parts of the transaction with different SIGHASH modifiers. And the point here is, in that exercise, I can generate the HD wallet from just one cell with those commands we saw before. Actually, this is not the one I wanted to show. There we go. So the one thing that I wanted to point out was, as I sign these transactions, I necessarily need to query the server for the previous output, which is going to be part of the SIGHASH. So that's an online operation, and I can do that here by just calling a bxfetchdx, and it's currently configured to fetch that from a test server, which is offered by the Libbitcoin team. Okay, so one more. So I can also use the library if you guys are new to the project and want to just dive in and see what kind of utilities you can get out of it. One of the things that you can also try, for example, is the script machine, which is pretty neat. So that's obviously used on the server side to validate transactions, but I can use it, for example, and here again, this is a Jupyter Notebook example. I've got the C++ kernel installed, and what I'm doing is I am providing, I'm just running a transaction through the script machine, validating a input. Let me just increase that a little more. In this case, it is a pay-to-witness program wrapped in a pay-to-script hash output that I'm spending. And what we can then see is how the script machine actually runs through the different script runs, right? I have an input script run, there's a stack state that I carry over, there's an output script run, and then the pay-to-script hash pattern is recognized, and then it's put on, it's evaluated in the third step, a pay-to-witness pattern is recognized, and so the pay-to-pubkey hash script is then expanded. And these are really nice, internal features that you can expose to the library. So just with a couple lines of code, I can evaluate that transaction that I've created, and I can get the different operations, the stack state after each operation. I can see what the script machine is doing. It's moved on to the output script evaluation. It detects the different pay-to-script hash patterns. Witness program is detected, and it evaluates, and then eventually evaluates to true. So from a learning point of view, that's a really nice thing about the library. Okay. So next, I'd like to talk about the server. So we're moving on to the server stack side of things. Can you move one slide? So on this, maybe back one. Thanks. So as I mentioned before, the design of these server interfaces is really meant to be a public one. So I'm trying to contrast here Bitcoin D. Bitcoin D initially designed as a home validating server, and there are a lot of functions there. For example, the wallet app, which aren't really meant to be exposed publicly. Obviously, right? Your keys are in there, and so on and so forth. Over time, as I learned yesterday, like Electrum server, over time, a lot of sidecar applications or servers have used the wallet app to import keys and to get that kind of functionality, indexing, which is not available through the other RPC interface. But generally speaking, it's not something that you want to expose publicly. So Libbitcoin is really designed as a public server, right? We've got a ZMQ interface. We've got CurveCP implemented. I can generate these pub key certificates through Libbitcoin Explorer, and I can have a secure connection. And you know, I've given this talk a couple times, but I wasn't always happy with the way I explained why it's a robust public server. So I think in the next couple slides, it makes sense to give a couple detailed examples of how ZMQ works and why it helps, like why it makes Libbitcoin hard to crash, right? I can publicly expose it like the Libbitcoin team does, and people can use it, but it's very stable.
Can you use Libbitcoin to do a chain analysis on the blockchain?
Generally speaking, yeah. I mean, you can follow the different spending graphs, and I don't see how that would be different. Yeah. I can show, yeah, okay, cool. Yep, thanks, Michael. So why is ZMQ robust as a messaging framework, right? So I've got an example here. We're on the client side. We've got a ZMQ dealer socket. And when I actually connect to an endpoint in ZMQ, the actual status of the connection is abstracted away. So the server endpoint could be offline, right? But my application doesn't necessarily see that. I connect to an endpoint and the code moves on. And so in this case, I'm trying to send a message, but the server is still offline. Maybe move one. And so what's going to happen is we have internal queues in these ZMQ sockets. So it's just going to queue internally, right? That's not something that's visible to the application. And at some point, and this is really important in ZMQ, we've got these high watermarks. So the queue, if it had no limit, obviously you're just going to eat up more and more memory. It hits that high watermark, and on the client side, my send operation basically blocks. So I can't send until that internal queue dequeues somehow. And that happens when the server socket comes online. The server socket comes online, and so again, we're on the client side, and it will just automatically connect and naturally dequeue, and my socket send operation then can continue. When I'm receiving, so again, we're on the client side. When I'm receiving, I also have a queue for the receiving side. Again, there's a separate high watermark that I can configure separately. So if I get bombarded with, let's say I'm a slow receiver, I'm a slow client, I made all these requests or I'm subscribing to something, and I can't keep up with the replies that I'm getting from the server, again, it's going to queue up, it's going to reach the high watermark, and what happens in ZMQ is these messages get queued on the server side, which is pretty nice. So there's no risk of my slow client of just queuing up messages indefinitely. So now we're going to switch to the server side. So the Libbitcoin server has a server socket. Maybe we can move on. Oh, sorry, not quite. We're still on the client side. But what's nice about ZMQ is I can very easily connect to multiple identical services, and I can balance the load or queries across them. For every connection, I have a separate queue. And what happens is it does it round robin, right? So what can happen is I might have a slow service. My first Libbitcoin server on the left side is a little slower than other ones. What can happen is I can potentially produce more queries than they can reply to. It's going to queue up, and once that queue is full, I'm just going to start round robbing across the other two connections. So that's all managed for me in ZMQ. From a client's point of view, I don't have to worry about that, which makes it really, really nice. So now we're on the server side, right? So what happens if one of the clients eats up a lot of the bandwidth, producing a lot of requests for me? This is built into ZMQ. On the server side, there's fair queuing, which basically means I give everybody equal opportunity in terms of producing work for the query, even though perhaps socket 3 is producing most of the queries or eating up most of the bandwidth. So if he tries to overload me with too many queries, there's not the risk that I have some kind of buffer overflow, because it hits the high watermark for his query, and then the messages are dropped automatically. So it just makes the Bitcoin really hard to crash, right? So I can publicly expose it, and that's just one of the design goals that was behind the server. Yeah, internally it also uses, this is really interesting. So internally actually also uses ZMQ sockets. Obviously these aren't TCP connections, these are all happening over shared memory. There's a ZMQ context that is shared. And so basically the internal communication happens over there. There are also shared queues internally. So if a worker can't keep up with, if a worker basically just dequeues the message, fulfills the query, executes the query, and brings it back. And if the workers can't work fast enough, the messages queue and eventually get dropped, as we saw before. The number of workers are configurable, so I can have multiple threads, so I can really nicely scale the performance of the query performance with more hardware, more threads. That's all done pretty robustly, all configurable. Yeah. Okay, so Neil Miller is working on adding 2 more endpoints. So he's added for, I think, version 4, right? Eric, that's scheduled for V4? Cool. To add a HTTP servers for WebSockets. So for ZMQ, let's say in your browser or your writing client, you know, they're plugins for every language. But having WebSocket interface is nice because then it's supported by the browser. It's native. And the query semantics is very similar to ZMQ asynchronous, so that translates pretty nicely. He's also added a JSON Rpc endpoint, which has partial Bitcoin D compatibility. You know, you can use the Bitcoin command line interface to query it. You get slightly different JSON responses, but that's pretty nice. So at some point, perhaps for certain applications, you can just plug in and plug out the different servers, and so that should be pretty cool. Okay, so one more thing about the server I'd like to talk about is the spender index. So you're basically indexing outputs or payments by address, and that's nice because we often see, you know, like Electrum or other projects, this index is being built outside of Bitcoin D. So obviously there's something useful about that. So here's an example. I want to build a really light wallet application, and I'm generating all my keys. Maybe I'm just, you know, restoring my backup for my mnemonic phrase, and for each key pair, I can fetch the entire history, and I look up by address, right, which is really nice. And I get all the outputs that were sent to this address. I get the spending inputs and the amounts, and so now I can obviously recreate the balance, but also the history of that specific wallet. So I can keep my wallet application really light, no indexing, nothing, just key generation and a couple queries. Yeah, so I think, as I learned from Chris yesterday, like Electrum Personal Server, the way they would do it, or the way it works there is, I have to import the key into the Bitcoin D wallet, and then from there I can get the history. So it's,
you have to rescan.
And you have to rescan as well, right? So, yep. Thanks, Michael. Yeah, maybe I'm a payment server, and there's a nice query which is we're still at the spender index, so I can subscribe to a specific address. So let's say I'm generating all these invoices for my payment server, and I want to, you know, for better UX, I want to know when the transaction is actually being broadcast or accepted into the mempool or the unconfirmed transaction pool, and I want to know when it's confirmed. So I make one query to subscribe for that specific address, right? And then once it's in the unconfirmed pool, I get a notification. Michael? Yep. And then I get a second notification, Michael, thank you, when it gets confirmed, which is really nice. So that's another example of where this can be very, very useful. And then finally, if you want a little more security, maybe you want to create a SPV client. Again, that's also really nice because I have my wallet in my client. I want to know the history or the transactions that I need to prove that are in this strong chain, and I can do that. I fetch the transactions related to the addresses that my wallet controls, and I build my header chain. And there's Libbitcoin has a pretty cool chain state class, and the way it works is Eric explained to me this. It's pretty neat. So if I'm a client and I want to validate the proof of work in my header chain, I can just promote that chain state from height to height by just including the next header. I don't need to, for things like fork activations or for retargeting, I don't need to look up previous blocks. And as a light client, I can't, right? I would have to query the server. So on the client side, I can do this entire header validation with just the headers and the chain state, and that includes forks and retargeting. So that's pretty cool. And yeah, obviously I'm gonna want to prove that the transactions that I'm interested in are actually included in the headers. Okay, so that's server performance, scalable, public server design, and spender index. Those are one of the key, I think most of the key takeaways. The next part is about the node. So that's where the validation is happening. The server just sits on top of it and provides the interface for the client. But the node is where the Libbitcoin team is doing a lot of optimizations to make validation faster, cheaper, and really help push validation to the edge of the network. So real quick, this is the network library. Asynchronous, and the interface to the application is this one PTP object. So you instantiate this PTP object, and it automatically starts a seed session, fetches the address. From these address lists, it will batch connect. That's pretty cool. So it will pick, let's say, 5 addresses, five endpoints, connect to them all at the same time concurrently, and the one that responds quickest is the one that will be used as a channel. And as the application, let's say you want to broadcast a transaction directly on the PTP network, all you do is instantiate the PTP object. You let it start the inbound, outbound sessions, seed sessions, inbound, outbound sessions, and the number of channels for all these sessions are configurable. So you can decide where to seed, how many channels you want to keep alive, how many channels you want to broadcast to. So that would be one use case. I want to broadcast my transaction directly on the PTP network. You might want to do some traffic analysis. There are a couple things you can do there. You can also subscribe to channels, messages on the channels. So you might say, whenever I receive a specific type of message, I want to query, I don't know, respond in a certain way. The actual protocols, so the P2P module or the PTP library provides all the protocols that keep the channels alive, right? Ping, pong, address. For broadcasting or propagating data, those protocols you'll find in the Libbitcoin node library, which inherits from the P2P network. Okay, the database is really cool. It's and I just learned about this late last year, but the database is implemented specifically for Bitcoin. And there are a couple of core ideas there which are pretty neat. It's implemented as a memory map file, so it's just virtual memory. It may or may not be in memory, so the OS actually does the I/O behind the scenes. And so if your memory space is large enough, potentially all the data could be resident in memory, which allows for very fast querying or very high performance. It is append only, so every time you want to add data, you allocate more space, and you just append, and you never delete. So let's say you want to write. I've got an example here. Maybe we can do 2-3 steps. The allocation is obviously guarded, but once I've allocated this space, the thread can just start writing into the allocated space. It can't be read yet because there's no link. For example, in this case, we have a header for the hash table. Since it's not linked to the header, there's no way another thread could read it yet, so I can just write in parallel. And this becomes useful in other optimizations. For example, that's a couple slides down, where you try to parallelize, block downloads, and you want to store them concurrently into your database. Let me see. Yeah, that's the database. Maybe we can skip yeah. So now we're linking, yeah. So one of the bigger optimizations Eric's been working on for a while now is parallel block download. And I think one of the core ideas is, how do you parallelize a task? To make something faster, like how do you parallelize a task that's inherently a sequential one, right? So you want to a blockchain is a chain of blocks. So to be able to validate the next one, you have to validate the one before. But there are a couple ideas there which are pretty nifty. So one is obviously I can once I've established the strong chain, the header chain, I can get the blocks in parallel. There's nothing preventing me from doing that. So that necessitates the ability to write the blocks in parallel, which we saw in the database design before, right? So these things kind of come together nicely in this part. Yeah, previously there's the idea of also validating in parallel. So you know, for many transactions, if you have a standard input, the standard input kind of tells you what the output would look like. So you can actually validate without having you can essentially validate some transactions in parallel without knowing whether the UTXO is actually in the list or not. But that doesn't work for SegWit, and I was talking to Eric yesterday, and you're telling me maybe that won't be implemented, but it's a pretty cool idea. I think it's worth sharing that there are some aspects of validation which can be parallelized, which was not obvious to me before. So there's then the validation chaser that moves up once I have a continuous set of blocks which are pre-validated partially and stored. I can then build the indices and do the final validation. So I think one of the takeaways here is a lot of things had to happen for these kind of optimizations to be possible, like in the database, like the design of how data is structured and stored to disk. And that just kind of ties back to the principles of Libbitcoin, trying to architect something that's performance, scalable, and hopefully reduces the cost of validation so we can all validate more and push it to the edge of the network. That's really the end goal. Yeah. Cool. Thanks a lot. That's the end of the talk. That'll be it. Yeah. Do you want the mic?
Any comments I make means I just didn't review thoroughly enough when you gave it to me before. I just highlight a couple things because people may be wondering. So James mentioned repeatedly it's a great Libbitcoin server is a great public server. And so if you think about it from a security standpoint, what does that mean? It means you're basically making trusting wallet stuff, right? If you're doing wallet stuff, if you're using a public server, you're not running your own node, you're trusting, and that's not great. So I want to help people better understand what our perspective on that is. A lot of things are very useful from a public server standpoint. For example, broadcasting a transaction. Connect to one of our public servers using Tor, send your transaction. It shows up in a community server. Anybody could have sent it there because it's a community server. Using Tor, the server itself can't identify who sent it, so now it just shows up in what people call the memory pool, right? The transaction pool. And that's what you want. You want your transaction to show up in the transaction pool, be anonymous at that point, and then people can share them, no problem. You don't need Dandelion or any other nonsense, right? So we try to keep that very simple. We're not trying to create internally to Bitcoin an anonymizing network. Just use simple existing anonymizing tools like Tor and a public server. So public servers can be very good for that. Also things like block explorers. If you're willing for the purpose of a block explorer to trust a public server, great. You can do a lot of cool, interesting things, chain analysis, whatever, to the extent you trust it. But ultimately, we don't want to trust these things. Want to verify. So the Libbitcoin server can be a remote private server. It can be a local private server, or it can be public. The same server can serve all those functions. There are a set of endpoints that are public, which means they're not encrypted. There's no point in encrypting them really unless you care about the information that's coming over the wire, and then you probably care about it if you're running a wallet, and why you're doing that with a public server, it doesn't make sense, right? So the server can actually authenticate the client. So you could set up your own server, put your own client public key in the server. Client has its private key, and now you've got basically the equivalent. It's using Curve CP, which is Bernstein's modern kind of replacement for SSL or TLS. So you have ZRMQ with Curve CP layered over it, which gives you all the characteristics of packet level privacy, server authentication, client identification. So you can basically make it the server for your wallet locally, in process if you want, out of process remotely, doesn't matter. So it's fully scalable from local embedded node with the wallet all the way out to being a public server for whatever scenario you want. But it does operate very nicely as a public server. I just wanted to make sure that people understood that trusting wallets is not really what we're after. The other thing I wanted to point out was you'd mentioned spender database, right? And the description was largely around address indexing, right? So there's actually 2 indexes, which I'm not sure if you're aware of, but there's a payment index, which we currently refer to as an address index in v3. In v4, it's called a payment index because it will index all payments, not just standard address-based payments. And it's using Electrum and ElectrumX's indexing mechanism, which is pretty straightforward. It takes the output script, SHA-256 hashes it, and stores that hash as the key in one of our hash tables. So now you as long as you can reconstitute the output script, which you must do even if you're looking at the input script, then you can recover all the payments to that address, which means SegWit, non-SegWit, standard payments, and non-standard payments. So that's the address index. But there's also something called the spender index, which is actually different. And in v3, we have another table which maintains this. And this is the reverse referencing of, so if you have a given output and you want to know which input spent it, it's a linear search through the entire blockchain to find that if you haven't indexed it. So we have an index for it. In v4, we've actually used some optimizations to eliminate entirely the table, which is a very large table, and just rely on existing information in the chain metadata to be able to provide this query. And since it's not a validation query, you don't need it. It's not used in validating. It doesn't have to be maximally performant. So we took a little bit of a performance trade-off there for people who are doing chain analysis, whatever they're doing, to eliminate like a 75 gig table, which was really nice. Still constant time query, still very, very fast. Just a few more steps. So yeah, we have an address index, a spender index, and then your basic transaction block height indexes as well. Anyway, cool. Thanks for putting all that together. It's great. Any questions for James or either of us? Your time.
So Libbitcoin has this different data structure where it's append only, as you said, and that makes initial block download much faster. But on the downside, you can't prove. Have you ever thought of combining Libbitcoin and Bitcoin Core in that you use Libbitcoin for the initial block download, and then use Bitcoin Core when you want to prune, when you're finished initial block download?
No, because we don't want to prove it.
Why not?
Because people can't populate the chain off of you. If everybody prunes, there's no Bitcoin.
Right, but so Bitcoin security model relies on having lots of merchants. And if some merchants don't want to have lots of hard drive,
then you're probably not interested in running Bitcoin.
That is true,
This
but
is what we're talking about, right?
but disk space is one of the only resources that perpetually grows. So like bandwidth is always one number.
It grows so slowly that it will be, and this is what Satoshi actually said, he's correct, it will be overtaken by some Moore's law, something.
Okay.
It's inconsequential. It's not, so we spend an awful lot of time optimizing certain things, a huge amount of time, but we don't spend any time optimizing things we don't want to optimize, right? If there's a feature out there that if everybody ran, everything would break, I'm not going to implement it, right? So for example, there's been a couple of these features that have been proposed. You can put out like great feature as long as as long as nobody uses it. What was it? Bloom filters, right? Like everybody running light wallets, nobody validating.
Yeah.
Right? I mean, you don't want that. Why would you implement that? So yeah, okay, mobile wallets are great, but if everybody does that, nothing works. So we just continue to move forward on making the node and server wallet more and more efficient, and letting just expected hardware gains to continue to advance to the point where these things can run on smaller and smaller devices, platforms. And that's inevitable unless somehow people stop running Bitcoin and they start running some coin that's got monster blocks. And then, all bets are off. So pruning to me is just like, it's a nonsensical proposition. Why do we want to build a node that prunes if no other node can then bootstrap off of that node?
Well, the point
I
of
don't want
nodes
to
is,
incent that to happen.
as you say, the main point of nodes is to validate the consensus rules. So you could imagine a system where some people prune because they have to, and other people who don't have
Well, you
to
can imagine a
prune.
system where everybody prunes.
Yeah.
And you can end up
You
more
could, but
like what's that big coin that everybody runs?
Ethereum?
Actually, my mind is that bad, I couldn't remember. You know, where nobody can actually run the chain. And that's just not, I mean, yeah, somebody come up with a system where we don't need the chain in order to, you know, validate the chain, then that's great. But right now, it's not possible. So I just don't, you know, to me, the optimization we're talking about in terms of disk space savings is nonsensical. I mean, even a prune node doesn't run on your typical mobile platform. So what are we optimizing for? Small desktops that can't hold, you know, 200 gigabytes? That's like $5 worth of storage.
That's true.
I mean, we decided to optimize against HDD, right? Amir made this decision before I came along. He says, why are we optimizing for hard disk? They won't even be around in a few years, right? Get rid of it. Who runs a hard disk drive anymore? Anybody? But when we started, everybody, you know, that's all there was, right? But he said, no, just won't do this. You know, we won't do this RDBMS stuff and this complex database stuff. We'll just do. It was his idea to do this, memory map files, and I've spent an awful lot of time on it, trying to get it to the point where I could be fully parallelized and all that stuff. But it was, you know, that was a sound decision. It has some significant trade-offs in terms of fault tolerance. So we're not optimal for, the server is not optimal for desktop logs, but right now we're not optimizing for that. So anyway, it's, I don't know, that's always my answer when it comes to pruning is we don't care about pruning. It's complicated, it's detrimental, it's not necessary, it's not saving that much money.
Speaking of optimization, the fact that you can do the parallel validation of blocks, is that potentially a denial of service vector? Can you get swamped with
No. Well, in order to, it's a complicated system, and explaining it takes a few minutes. But parallel validation means a couple different things. Like, so when you validate headers, you validate some aspect of the block, and then say when you get the whole block, you can, without the preceding blocks, you can still validate. Like there's context-free validation in a block. Is it too big, right? Does it have too many SIGOPs? You know, does it have duplicate transactions? The transactions are in order. There's a number of things that actually are validatable, independent. So we do context-free validation in parallel always. It's no problem. When we bring blocks, we download blocks in parallel. So we have to wait until we have a sequence of blocks. Technically, that's over-constrained. You don't really have to wait till you have these blocks in order to validate. You just have to wait till you have all the previous outputs, which may mean you could miss some blocks, right, and still validate. Tracking becomes complicated and it's not necessarily worth it, but that's what's happening is like every generation we're actually taking that additional optimization step and actually doing it. So in this process, we don't store anything in memory for very long. And this is a very big, we don't have these big caches like Bitcoin Core does. Like I was careful before not to use the term memory pool. People refer to the memory pool. Well, it's only a memory pool if it's stored in RAM, right? We don't have a RAM pool of blocks or transactions, so we don't have a memory pool. We're like, well, there's no memory pool. No, we have a transaction pool. It's a pool of transactions that are not confirmed. So in other words, we're bringing out all these blocks. We're not just holding them in memory, waiting until we can get them in order, and then actually putting them on disk. We bring them in and we put them directly on disk. So where's the DOS vector? Just because we're doing it out of order doesn't make it more DOSable. If we did it in order, it's just slower, right? Now, potentially if you validated the whole header chain, you've got proof of work for DOS protection, right? So you wait till you have a current header chain, and then current meaning some time differential from the current time, which is configurable. We use 144 blocks, I think. And then, and once it gets to that point, we've got the strongest chain we've seen. We start downloading. We download them all in parallel. Each peer gets 50,000 blocks and up to the amount of peers we have. And then it's all kinds of stuff we do to optimize that, like using standard deviation for peer performance and dropping peers if they fall below like whatever 1.2 or whatever the configured standard deviation is, below the norm. And so basically it gets faster and faster and faster as it's downloading, which means it's putting a heavier load on higher performing peers, which is what you want, right? And dropping lower performing peers, which is also probably what you want. We don't do that during header sync because we want all peers to kind of be able to have equal input to the set of valid into the strong chain. So the header sync's actually kind of slow. So we get all the headers, we have DOS protection, we bring the blocks down in parallel, and potentially some block that had valid proof of work is invalid. So we validate and go, crap, this is actually an invalid block. So that whole header chain is now invalid, and we deal with invalidating the header chain. But again, proof of work is providing the DOS protection. Right? If it's very expensive to create that once you get to a current chain, at least in Bitcoin. So it's okay. Okay, they spent a huge amount of money and they got some space on your disk. What did they get? They got a bunch of headers, 100 bytes a piece with the metadata. So Bitcoin has inherent DOS vectors that are almost, I'd say they're impossible to eliminate. You know, weak potential chains. What do? You store them in memory, and as you build them up to try to see if they're going to be stronger, or you store them on disk. Anyway, so continuous parallel initial block output is great. The weakness of it, the difficulty of it has been that last step of fully validating against the previous outputs, which we do sequentially because doing it more, less restrictive is much more complicated than it's probably worth. And we don't attempt to do the smaller amount of parallel script validation that we could do because it's just more complicated than it's worth. It's a declining value over time as well because of SegWit. But what has to happen is we have to kind of try, as blocks are all coming in parallel, we have to kind of chase up the validator to validate the blocks that we can validate. And what can happen is we could be missing one block, and it just, it doesn't come into the very end, but it's block number 2. That can be annoying. So we're continuing to optimize so that we can keep the validator moving as fast as the chain. Because oftentimes what happens is we can download the entire blockchain, store it in 10, 15 minutes, right? No problem. I mean, we're talking with all the validation done except for script validation, basically. And then we've got, then it can, you're reading them all off the disk, you're validating, and that can take a long time. So just completed before going out to my last travels, a change that allows us to basically parallelizing the reading of the blocks off the disk that we're going to validate before we validate them. Because it turns out that read cost is actually the biggest cost. It's almost like re-downloading them off the network. So we download them, we store them, read, write, read, validate, update. So that read is happening sequentially along with the validation. But the validation is fast, the read is fairly slow for that big block. So what I've done is done a read ahead cache, which basically takes as many threads as you have, and it just reads ahead the block. And so basically now the validator screams up and goes a lot faster. So that looks very hopeful to get that, because we're really trying to get it down to 30 minutes, an hour at the most for validating the entire chain. But chain keeps getting bigger.
How does that window work to ensure that the chaser has continuous blocks that can just continue validating? Is there some window that you
can't ensure that you're going to always have the next block if you're going to download the blocks in parallel.
Right.
What you do is you ask for them in order, and if you have a slow peer, you drop that peer, and so you're likely to get them in order eventually. You don't get them in order, but you're going to get the early ones earlier and the later ones later. That does work out pretty well. The problem is you'll have jumps, right? Like there'll be a gap and then another gap, and so once that gap is cleared, now you need to go read all the blocks you actually do have. You might have the next 10,000 blocks, right? You're just missing one. But you have to read them sequentially, so you can validate them sequentially. That doesn't, I mean, we actually don't validate sequentially. In the block, we parallelize the validation, right? Because now we have all the previous outputs. So we actually fan out, we parallelize validation in the block, but we're reading on one thread the entire block. Like, that doesn't make any sense. We can read, so we basically fan out and read ahead all the blocks that we can read, and then as blocks come in to fill the gaps, they just get cached. So the read ahead caches blocks as they come in, as long as they fit in the window. And then if they fall out of the window, then we read them ahead when we catch up to them. So it's complicated. That's why these optimizations weren't done in the past. I mean, you look at Bitcoin Core, there's no way you can even try to do this, right? The store is not parallelizable. The code's too complex to refactor this way. So for us, the code's actually not, the code itself is not complex. It's getting it's figuring out what you need to do and getting it all right. Once it gets done, you're okay, oh, that's pretty simple. But this one feature, this continuous parallel block download, has been the thing that's held up version 4 for quite some time. It's a big issue.
So would you say, as a complete newcomer to trying to start contributing to Bitcoin in like software development wise, this would be an easier learning curve than working on the coin core?
Absolutely, yeah.
It's like much more well-factored.
Yeah. There's a separate library for, I don't know if we bring up the library slide, but there's a library for system primitives, there's a library for P2P, there's a library for the interface. They're actually in separate, libraries. So they're very well factored. There's actually a consensus library which we use to bring in Bitcoin Core's 33 consensus critical files for script only. Yeah, so that's this one down here. It's optional. These dotted lines are, the dotted arrow is an optional dependency. These dotted boxes are external dependencies, right? This is actually our library, but it just wraps 33 files from Bitcoin Core.
That's going to be my next question, is how do you make sure critical consensus code stays platform compatible?
We don't. Just like Core doesn't, right? Between each code change, there's a potential consensus break from the last code change. And as you've seen over the years, there are
the reference client. Do you see becoming the reference clients?
We have been the reference client. There was another client that was built using ours as the reference because Core was too complicated and they couldn't figure it out. It was like the Rust implementation.
Yeah, I'm not a C++ developer. I want to start.
Yeah. Well, I
was confused as hell.
If you want to learn some single aspect in isolation, of Bitcoin, and you want maybe, or all of it, whatever, the Bitcoin is a heck of a lot easier. So for example, script, you can go through the script code and you can it's obvious, right? There's a boom function for every little script function, and there's a big switch and loop, and it's as simple as it could possibly be made. And I've spent time, I don't go into, none of our code is from Core, it never was. It's all been written from scratch from the beginning, starting in 2011. And, but in order to confirm consistency or just to find out what's going on in the network, sometimes I go into Core code, I'll be like, oh my God. I spent hours just trying to figure out what the stupid little loop is doing, There's, and some of Satoshi's wacky bugs are fun to track down too. But, we can't, nobody can guarantee consistency of implementation on any software that's nearly this complex. That's really that's a non-goal, right? We just implement the code the way we think it's correct. For example, we have a database that's 100% faithful. We know what we put in, we're going to get out, unless there's a disk failure or an underlying hardware failure. So, but as core proof, by using some external library that's massive and unpredictable, it's not the case in Bitcoin date. At least it wasn't, and I think you could argue it's still not. So which one's right?
It's perplexing that Bitcoin Core is still like the nexus of Bitcoin development.
It's just,
it shifted to.
it's like saying Netscape was the nexus of browser development. It was, because it was, the Mosaic was first, and Netscape was built on that, and everybody used it, everybody looked at it. It was what defined the standard, and then eventually it wasn't, right? And it was IE, and then, it was.
So you're the IE of Bitcoin.
It was IE. No, it was something better than Chrome. It was Chrome. No, it was Firefox, it was Chrome, right? I mean, people tried to resurrect, Netscape into Firefox. Yeah, I mean, things evolve. It's, I don't know if we'll ever get, that popular, but, our objective is to provide what you want, what a lot of people want, is just be able to look at the code and understand it, and do different things with it. Libbitcoin's a library. It's not a monolithic application. It's designed for building other stuff. It's a different design objective. It's also designed for readability. So we do make performance trade-offs sometimes for readability. I mean, they're absolutely trivial. We work very hard on performance, but sometimes I'm like, no, I'm just not going to do it the way they did it, because it's just, it makes it completely unreadable, and this is no reason, right? It's just such a trivial performance difference. So there's a heavy emphasis on code readability, understandability, maintainability, testability, deployability. You see, look at our dependency graph. It's almost nothing, right? When we started out, a few years ago, we had like 15 dependencies, like all these external dependencies. It's ridiculous. Could never deploy it.
We also have that reproducible build system that Bitcoin Core uses, where you can
Deterministic build?
Yeah.
Yeah, we don't have a deterministic build. That's just a lack of manpower. We don't attempt to do it. We have, we pretty much everything else, continuous integration, continuous test coverage monitoring, and for Windows and Macs and Linux and Unix. We have a code generation. We have one of our libraries. It's not up there. It's not part of the dependency graph. But the Bitcoin build is a build system that generates all of the build artifacts for all of our libraries. So in other words, when you write code, you just write the source code and run the Bitcoin build, and it generates all the make file, all the CMake stuff, all the Visual Studio stuff, everything. All the test, all the Travis stuff, all the cover, all generated. So we put a lot of time into.
On Windows, or actually use Linux?
No, there's a Visual Studio builds, not just Windows, but actually Visual Studio builds. No. Yeah, actually we don't support yet Windows builds except for Visual Studio. We don't have like the Sigwin builds, or what's the other one? Making NGW. We will, but we just haven't. That's just going into the Libbitcoin build and generating more, build files. Also, we've got people that do these things exist. I mean, people have done it. People have done like Android. I don't know what are the other embeddable chip stuff. There's also been. I can't remember. So there's people that do things like that, and then they come to say, "We did this. We want to put it in your system." Like, okay, let's write the code generation, right? Because we're not going to manually maintain these builds for all these platforms and manually test them and everything. So basically, we don't let stuff into the system that's not going to be maintainable. So we're gradually getting it in. We got CMake in last year.
So you're telling me I can clone the repo, open the Visual Studio.
Double click on the solution file, open it up, compile it, and run it. Yeah, that's what I do. Yeah, I do all my work in Visual Studio. It's a great debugger. Yeah, all that concurrency, parallel work in the P2P code and the server code, and the database code. Yeah, I use Visual Studio. And then I commit the stuff to the Travis build, and it tests it on Linux and OS X, and it works, and it's good. So I rarely get on my Linux machine. I almost never get on that, but it still all works. We don't yet have Xcode project files. The plan is to have Xcode project files, to have NGW, and also to maintain Android and one of the other chipsets. I can't remember. But it's just somebody's got to write the code generation and set up the continuous integration for it.
Who's funding this development?
Who's what?
Is this purely voluntary?
We've had, I funded it, well, I fund myself. I mean, I don't get paid. So I've done it for 5 years. And funded a guy he did it himself for about a year full time, and then I paid him for about 2 years. And then we picked up support from a miner for about 3 man years. And right now we're looking for new sponsors because I've got 2 full-time guys that may not have a sponsor, not including myself, and 2 other guys that I want to bring on full-time. One of them right here, but we haven't had sponsors yet. So if anybody knows anybody that wants to contribute to the Bitcoin development, send them my way. It's one of the reasons I go out and do these things. I always forget to put the pitch slide out, but you know, it's there's this guy here too. These 2 guys. Number 3 and 4.
Obviously wealthy from having bought Bitcoin early. You should feel compelled to try and sell it.
Maybe they do, man. Oh, it's all on. All right, any other things that we can answer?
I was curious about what kind of hardware you are aiming at. Like, you know, what is bottleneck in the speed? Is it bandwidth? Is it the number of cores?
Speed of what?
Of downloading and validating blockchain. You were talking about like in 10-15 minutes. I mean, that's just not just a desktop, is it?
Well, in all implementations, the hardware is not fully utilized, right? So in what scalability means is you add more hardware, you get a linear improvement in performance of whatever the thing you're trying to scale, right? So people forget that. That's actually what scalability means. So you add more hardware, you get more speed. So we try to design Libbitcoin so that if you add another core, you get a proportional increase in performance. You add more memory, you get so for example, it's very what's the bottleneck? So network, memory, CPUs. Usually it's the code. If it's the developer time, it's the cost of making these optimizations so it'll be fully scalable. Like, you know, when you're syncing, sometimes it's your peers, but you can manage that. You write the code properly, right? Like we use this deviation measure so we can kind of weed out the slower peers without having to hard code some kind of speed expectation in. With core, it's got a non-parallel database. You can't write download blocks in parallel, or at least not a significant number, and don't store them in parallel. But you know, as we know, even if you do, you have to be able to validate them still. So again, more complicated code to pull all that in parallel, do as much validation in parallel as you can, and then sequentially validate what remains. Once you're doing all that, once the code's all written optimally, there's no single bottleneck. I mean, CPU matters, memory matters, network speed matters, pure speed matters. And theoretically, what you do is you find out which things holding you back, and you add more hardware. Then you add more hardware on something else, and add more hardware on something else. But eventually you get to the kind of theoretical limit where you can't factor the work up anymore because the dividing of the work has a cost, and you reach a limit on that too. So sometimes it feels like that's what we're approaching, right? Like you can't fan out to 64 cores because the fan out cost is not worth it. So you're kind of reaching the limit of how many cores. You can't get much. Like I have a 256 gig machine, 64 cores. I have 2 of them, and I have a Linux and a Windows box, and I use these to kind of test where these limits are. And when the chain fully indexed is 200 gig, and you got 256 gig of RAM, you're basically keeping the entire chain in memory all the time. So there's no disk. So disk speed becomes irrelevant, right? We're giving the memory in that file system we're talking about. At some point, probably well below 256 gig, it becomes irrelevant. So that's cool. Okay, we've got we don't have to worry about the disk anymore. It doesn't matter how fast our disk is. We got enough memory. We don't need any more memory. No more memory is not going to come. So now what do we need? You know, okay, well I can't use any more than 64 cores or 32 cores because performance starts to drop off with factoring. So I can get a faster network. I'm sure that would help. At my house, I crashed my router when I connected 5,000 clients.
So did you test Bitcoin Core on that machine? Like how long does it take for it's going code to validate from the chain?
It depends on who you ask and what machines you run on.
Yeah, yours.
Blocked about it recently.
Yeah, there's a lot of
And I think it was under 2 hours.
Yeah.
Start to finish.
if you don't validate, yeah.
No, it was fully.
No, they don't validate anymore. They don't fully validate. They use milestone, what we call milestones, which is if you see a well-known block, you don't validate anything prior. It's the latest Bitcoin core stuff doesn't validate anything except the very tip. Yeah.
I think
They went from 6 hours to 2 hours by doing that. Yeah. So the question is, where do those milestones, where do those well-known blocks come from? They're putting them in the code, right? You really should validate the whole chain yourself and then say, okay, I know this is valid, this is a well-known block, and then put that in yourself.
Is that okay? So Bitcoin Core, but like essentially new Genesis.
You can look at this. You can look at. The easy way to do it is look at the CPU when it's validating. It's completely flat. It's not validating, right? And then boop, at the end it jumps up. If you're validating and you're doing it maximally, like optimally, you're going to be 99% CPU all the time, right? It's a CPU intensive process. You're running scripts, right? So what I saw was when they made that change, that it went from so you can. We haven't implemented that feature in V4 yet. We're going to do the same thing, but the question is, we call it milestones, which is consistent with the idea of a checkpoint. You know, on the road, you have a checkpoint, there's cops, right? Or you have a checkpoint, and then a milestone is like a marker on the road. So one prevents you from going through unless you are a certain block, and the other one is, oh, if I see this block, I can skip the validation. And that's what they're doing, and it makes sense if you want to trust the hash for that. But the question is, who gets to decide what's a valid chain, right? So they don't force you through that chain, which a checkpoint would, which is bad. But choosing those optimizations are.
So it should always remain an option, and the default.
I think it is an option, but I think by default it's on.
I think so. Bitcoin Core by default, the optimization is on.
I don't spend a lot of time in it, but I'm pretty sure that every time there's a release, they're updating the well-known blocks. They've done some other things to optimize as well, and it's gotten a lot faster. I don't benchmark against them. I don't spend a lot of time.
Have you got a benchmark for how long it's taken for a full sync from a brand new node on like a very fast bandwidth internet connection? You got 256 gig memory machine.
Yeah, I mean, a year and a half ago we did the whole. We validated under a milestone or under a checkpoint, right? The whole entire chain in 15 minutes on a fast local network. Yeah, again, but you're skipping the costly validation when you're operating under milestones, and that was like about a 400,000 block chain. That was how far back that was. So that was our prototype, and we didn't want to use milestones. We didn't want to use checkpoints to do that, right? Because then you're out of checkpoints and you can't do it anymore, and you're also relying on checkpoints. So we implemented a totally different approach, which was to rely on the header proof of work, strong proof of work chain and currency, to then, once we get to that point, then treat that as a set of blocks that we can download in parallel. But then actually performing the validation has a significant cost, and you have to do that to some extent if you don't want to rely on somebody else's telling you what the valid chain is. We also need to. So our server does indexing that Core doesn't do. Core doesn't do transaction indexing by default. You have to turn it on, and that changes those numbers quite a bit. We always index all transactions. So you would have to turn on transaction indexing to get an apples to apples comparison. On our server, we index all payments and all spenders, which is basically like Electromax plus spenders indexing, which is like double what Electromax would cost. So it's not even close to comparable to what Core is doing. So to do a fair comparison, it's basically a node with milestones and not indexing, you're subtracting the transaction indexing cost. And we're right now, without the validation, we're probably somewhere around 30 minutes on my machine. but validation is significant. You know, it can take a few hours at this point without the optimizations that I've just been describing. So I don't know. You know, since this is ongoing work, it's kind of hard to benchmark it while it's in process.
I mean, anything less than a day is pretty
Yeah,
good.
my goal was to get it down to, originally it was to get it down to less than 30 minutes. Now the chain's 100,000 blocks larger, and I'm happy with an hour. So that's kind of my target right now. I don't know if we'll get there, but it's worth trying. All right, let everybody go.